So it looks like we are ready to get started. So I'm going to hand it over to our first speaker, Ben Bright, to begin.
So I'll be talking about mapping fuel with airborne LiDAR in Arizona. And this work was supported by a couple of NASA projects, as well as a joint fire science program, FASME project. My talk will follow the traditional scientific outline. I'll talk about my methods and results. I'll talk about the study area, the data that I used, and a modeling exercise I went to relate the data to each other, the field data with the geospatial data. I'll talk about the results of those models, as well as the maps that I created from the models. And so in a nutshell, basically the objective was to use the airborne LiDAR to map fuel. And because we had multi-temporal airborne LiDAR, we were able to map consumption by differencing those maps. And then I also did an analysis of those maps, looking at them in terms of forest type and time since fire. The study area is the Kaibab Plateau in Arizona, just above the Grand Canyon. And it's a large area, and it spans a big elevation gradient. So there's a lot of different forest types. Down low, it's shrubland that transitions to pinyon juniper and goes all the way up to spruce fir forests in the highest elevations. And it's an area where there's a lot of fire. There's frequent both wildfire and prescribed fire. And there's a lot of recent LiDAR there. There was airborne LiDAR there flown in 2012, shown in that blue outline, covering a lot of the plateau. And then even more area was flown in 2019. And we also had 2020 LiDAR flown over a couple of fires that burned in 2019. So the point of that was to capture post-fire structure and vegetation. And those fires were the Castle Fire, the northernmost fire there in the center of the map. And then below that was the Ike's Fire, where we flew a portion of that extent. And we'd hoped that we'd be able to gather field observations to relate to this airborne LiDAR, observations of fuel. But because of COVID, we weren't able to. So Alex Spanuth made available, and local fire folks there made available a plot database, which was invaluable to this project and made it possible. So it was great to have that. So here's a look at the plot protocol. The point of the plots was to assess fire effects on vegetation and fuels, which is great for our project. So surface fuels were measured along transects that were 15 meters in length. As well, offset from that, the trees were measured as well on these plots and fixed radius plots, which is great for relating to airborne LiDAR. So we were able to use a total of 69 of those tree plots and 153 surface fuel plot points. And we used the plots that were, of course, coincident with the LiDAR acquisitions in space, and also temporally coincident as well. So I won't go into LiDAR too much. It's been spoken a lot about, and I think a lot of people are familiar with it. But just real quick, for this project, again, it was airborne LiDAR mounted on a fixed-wing aircraft, where the sensor is mounted on the aircraft and scans the landscape that way. And it results in these great point cloud data sets full of information about the vegetation below. So to turn that data into information for modeling, we used what's in LiDAR speak called the area-based approach, where we bin those discrete points in space into grid cells to make rasters. And we call these generally LiDAR metrics. And for this project, we use a 20-meter metric grid where we created those grids across the entire LiDAR extents. And I think of like a cookie cutter that depicted here on the right by a cylinder, you also generally cookie cut out points where you have those plot measurements on the ground, and we summarize the metrics the same way in those plot extents to produce metrics. And we produce both canopy based metrics where we use all the returns that are 2 meters above ground or greater. And we also, for this project, produce some understory metrics more near ground, with the goal of characterizing that more near ground structure. In addition to the LiDAR data, we used a couple Landsat products. I considered both using the Landsat burned area product from Todd Hudbaker, which is a remote sensing based product that gives you a burn probability for pixels, Landsat pixels. We also considered MTBS, just polygon data to get at fire history for the area. And ultimately I went with the MTBS data just because the Landsat burned area product grids were a little more conservative with their probabilities. And on some of our plots where we knew burning had occurred, the Landsat burned area product missed it. So it was throwing off our modeling. So with that MTBS polygons in the area, I calculated a couple variables, year since fire and number of past fires, because there was a little bit of reburning for the Landsat record. And then later I pulled in the Landfire existing vegetation type layer just to look at the surface fuels by general vegetation type across the plateau. So our response variables were these fuel variables measured on the ground, and our explanatory variables were the LiDAR metrics and the couple Landsat variables I just mentioned. To relate those two, I used random forest modeling, and one good thing about that is that you can get estimates of model error as well as estimates of variable importance. And through lots of iterations and a variable selection routine, I settled on final models and kind of looked at what the most important variables were. And after you have those models, then with the grids, the 20-meter grids, you can apply those models to create maps of fuel. And I did this for all the LiDAR acquisitions, 2012, 2019, and 2020. And for the Castle and Ikes extent, where we had the pre-fire 2019 LiDAR maps and the 2020 maps, I could difference those two to get consumption for those smaller areas. So on to results now. Observed versus predicted plots are on the right. For fuel variables that I predicted, available canopy fuel, just one canopy fuel variable, total surface fuels, and then I broke total surface fuels into 1 to 1,000 hour surface fuels, and then litter and duff. And I was pleased with the performance of the models. Actually, the surface fuel models, and in particular, exceeded my expectations based on some prior project that I did something similar with, and the literature. And the important variables shown on the left there, they also made sense. So for predicting canopy fuel, the canopy distribution variables were important, as were canopy density variables, which makes sense. And then total surface fuel, likewise, it was really nice to see the understory density variables were important to predicting that, suggesting that the airborne LiDAR was measuring near surface variation that helped explain the variation in surface fuels, so suggesting that it was directly interacting with structure down there. Also, canopy distribution was important to the surface fuel variables, and the fire history variables, while not the most important variables, also helped explain an important amount of variation in surface fuels. And lastly, maybe I should mention this first, elevation was a huge predictor, and in general, as elevation increased, surface fuels increased in this area. Also, mentioned litter and duff down there. Actually, that was the best model in terms of model performance. And in that case, of course, the LiDAR, airborne LiDAR is not directly sensing litter necessarily, or of course duff, because it does not penetrate the ground, but just the correlates to those, canopy density in particular, and then elevation and fire history were important to explain a lot of that variation. So here's what the maps look like. I didn't spend too much time looking at canopy fuel map, but this is available canopy fuel here. It was good to see, whenever you make a map, you just want to see, does it make sense? And it did make sense where we had the ponderosa pine woodland, mixed conifer and spruce fir forest here at the tallest part of the plateau. There was more canopy fuel. But there wasn't really a big difference between those different forest types, between the mixed conifer, ponderosa pine, and spruce fir. So really, it wasn't really forest type that created differences. It was just, how many conifers were there that determined how much available canopy fuel there was. The surface fuel maps, here's total surface fuel in 2019, were really interesting. I was very interested to see these, and my initial thought when I mapped this was, this is definitely following just what is the vegetation type there. Hence why I pulled in the land fire layer just to look at forest type and general vegetation type. And you can really see here that, and in this block spot down here, the ponderosa pine woodlands, the fuels tended to be lower and more variable compared to the mixed conifer and spruce fir forest type here up high. And you can also see fire scars here in the surface fuel map, and just variation in general with vegetation type. So my other thought once I produced this map was, I want to see, can I kind of tease out, will my map show differences in total surface fuel with time since fire? And that's what these plots are showing here for those different forest types. And there was a relationship. It was good to see, as expected, fuel increases with time since fire. And initially, and I should say this is from the whole landscape, predicted fuel cells are what went into these distributions. And initially I plotted a linear model just to see, what's the accumulation rate to these plots, but it became apparent, it's pointed out to me how there's this asymptote and it's more of a nonlinear relationship. So I fit a nonlinear model to it, an asymptotic model, and that did fit these data better. And just like I showed in the last map there, the ponderosa pine forest type, the woodland, surface fuels tend to be less, and the accumulation rates were also less compared to like the higher elevations, spruce fir, where surface fuel was greater, and also the accumulation rate was greater as well at the spruce fir highest elevation. So here are the surface fuel consumption maps for the Castle Fire and the Icke-fire, where we had the 2019 pre-fire LiDAR and the 2020 post-fire LiDAR. And it was good again to see that within the burn perimeters, consumption was either, as estimated with the maps, was either neutral or positive, meaning there was less fuel after the fire. And it was very quite correlated with burn severity with the DMBR raster for the fire. And here in the Icke-fire, there's this blue area showing not negative consumption, but that's maybe a misnomer, but showing where there was more fuel in 2020 than 2019. Initially, that was, that doesn't make sense. Yet it's easily explained by the Steina fire of 2018. You can see here in the burn severity raster that perimeter a little better. So it had just burned the year previous. And so it is actually very likely and that this area did not burn at all. And so there was, in fact, growth rather than loss. So in conclusion, I conclude that LiDAR did quite well here, predicting especially surface fuels. and that, these surface fuel maps are probably, of course, it's just a prediction, and they explain only 40 to 59% of the variation, but really did quite well. I was pleased with the performance. I think they are a fair representation of the surface fuels here. And those Landsat-based fire history variables were important to helping to explain this variation. It made a difference, particular time since last fire. And it was interesting to see, surface fuel and fuel accumulation was greatest at the higher elevation of the plateau. And our consumption rasters generally make sense. The consumption was either kind of a net of 0 or when it's up to as much as 10 kilometers per meter squared. And that was correlated with burn severity. And a lot of the motivation for this work was to create these maps of fuels and consumption so we could relate them to emissions data. Because for the Castle fire and the Ike's fire in 2019, an aircraft flew through the plume to sample emissions. And so in the future, we hope to relate these maps that I produced to this data for more analysis. And that's it. Thank you.
On with our next speaker, happy to introduce Andy Whelan. Take it away.
All right. Yeah, thanks. Thanks, Jessica, and thanks everybody for tuning in. My name is Andy Whelan. I'm a research associate at the Jones Center at Ecology, and I'm going to be talking a little bit about some research that we did following Hurricane Michael in 2018. Hurricane Michael was a surprisingly strong storm when it passed here in 2018. The eye passed about 20 kilometers west of us, and at that time it was weakening from a category 3 to a category 2 storm. That was surprising because it was 160 kilometers inland from where it made landfall. So after the hurricane passed, we went out and looked around to see what had happened, and we saw a lot of scenes like this where there's just a lot of fuel on the ground, and that was concerning to us because most of our management here is done with prescribed fire, and all those fuels make it hard to burn. There were also a lot of canopy gaps that were created, which might make it hard to burn in the future. So this is all another concerning thing, is that major hurricanes are forecasted to become more common in the future. So what do I have here? Oh yeah, I just wanted to talk about some of the problems that that all these fuels on the ground can cause. I showed the fuel jackpots there. Well, when those burn, they burn hot. They can cause damage to tree crowns, which will slow growth. And they can also create these big fire scars that weaken the bole and make a tree more likely to have a bole snap and fall on the ground later. The second picture there is incomplete burning or fuel shadows. This isn't a great picture, but we had some of these where that fuel just creates a spot of maybe high fuel moisture that doesn't burn well, or there's a log on the ground, and it creates just a physical barrier for fire spread, and the fire doesn't get there. And that's a problem for us because what our fires mainly do is control hardwoods. And so if they don't burn, they're more likely to escape into the canopy and change our kind of our forest dynamics, make it shadier and that kind of thing. Smoke issues. So down trees, they can burn for a long time. I've got a picture there of one burning, but at night those things will just burn and burn, and the smoke will kind of stay on the ground. And there's a couple of highways that go through our property, and we also have neighbors who don't like smoke, but smoke can cause a big problem, and you know, we don't want to cause accidents out on the highway. And then I mentioned canopy gaps. This little picture just shows some of those hardwoods that have gotten big enough that we're not really doing a good job of controlling them with fire. So those are the kind of issues that we were worried about, and you know, wanted to avoid. So we started looking for ways that we could kind of quantify the damage to the canopy and maybe identify spots where there was severe canopy damage. And we're lucky to be a neon site, and neon collects aerial LiDAR data. So we decided to see if we could quantify some of that damage with LiDAR. And this was, for me, it was my first time dipping my toe into LiDAR, so it was a big adventure. But LiDAR kind of works by its light detection and ranging. So a LiDAR scanner emits kind of a bunch of packets of light that go and bounce off of vegetation or the ground and come back to the scanner where they're sensed, and the scanner can get a distance on it by timing the amount of time it takes to go out and come back. And you know, if you sweep back and forth, if the scanner kind of sweeps back and forth as the plane moves forward, you get this this point cloud, which is a three-dimensional representation of your vegetation. And that seemed really good to detect changes on the vegetation, because you get a really good and accurate picture of what's growing there. So here's my just a kind of a recap of the intro. Fire is an important management tool for us. You know, it maintains our forest structure and maintains biodiversity. I should say that we burn every other year here, so we burn pretty frequently. Wind damage affects fuels immediately and into the future. That's that canopy gap thing. And so our questions were, can we identify areas of severe wind damage? And we thought that we'd be able to do that pretty easily, just because LiDAR sees the canopy so well. But we also wanted to know how accurate LiDAR is in southeastern forest types, and what forest types are more susceptible to damage. We have a bunch of forest types here. The Jones Center is mainly dominated by longleaf pine, but we do also have a lot of hardwood forest types and mixed forest types. So there's my hypotheses. We will be able to identify wind damage. The LiDAR estimates will be less accurate in mixed forest types. That's just because there's more variability in the tree forms there. And longleaf dominated forests will be more resistant to damage than hardwood forests. And that's just from the literature that kind of shows that longleaf are really resistant to damage. So I have mentioned several times, this study was done at the Jones Center at Ecology. We burn frequently. We have 9 forest types. They're pretty common on this southeastern coastal plain. And this little table is pretty busy, but it's you know, representation of the species for each forest type. And then we're also lucky to be a neon site, which provides publicly available data for LiDAR, which we could use for analysis. We had 864 field plots that are measured. We measure a quarter of those every 4 years. So there are about 216 plots that we could use for each year. But at each of those plots, we calculate wood volume from allometry for each species. The field plots are 18 meters in diameter. Aerial LiDAR was collected by Neon for us in 2014 and then 2015 through 2019. And we derived some forest metrics from that point cloud, which kind of, these metrics just describe the structure of the forest. These are the models we used to estimate, like we fit these models to the wood volumes that were calculated at the forest measurement plots. And we use these to estimate wood volume. The first is a multiplicative model that we found in a paper by Marc Bouvier et al. In 2015. And we were interested in finding really kind of a simple way to do it that would be adequate just for getting an idea how much change there was to the fuel. And so we just used a linear model that Chen et al. In 2007 also used. We validated our LiDAR estimates with the 2014 data. We fit the LiDAR models on the data from 2016 to 2019. And we used AIC to find the best model. Let's see what we got. So this is an overview of the study design. So we measured things with field plots, and then from those calculated wood volume, and then we fit models to those wood volumes using the metrics that we derived from the LiDAR point cloud. We use maximum likelihood estimation to fit the models. We validated on 2014 data, and then later we estimated wood volume site-wide on a 20-meter grid, just to see how well we could model, we could show where the damage was. And that's my next slide. So in addition, I probably should have mentioned this before, but we had a tornado in 2017 in January that crossed the property. And here I have that dotted line is the track of the tornado. And it quit being a tornado shortly after it crossed our property. But you can see there that those red colors are higher damage, and that really matched what we saw on the ground and gave us some confidence that that this was working pretty well. So that was nice to see. This was just a EF1 tornado. This is the difference following Hurricane Michael, and so you can see there's a lot more red there. It was a much bigger event, much more widespread, and much more damage. We had a lot of issues here. So these images really show that we can detect where damage occurred with LiDAR. And again, that's not too surprising because LiDAR really sees the canopy well, and it can see changes in the canopy. But we also get these volume estimates, and I want to throw out there that these volume estimates should be taken with a grain of salt, because we model wood volume change by taking the difference in wood volume between consecutive years, but it may be more accurate to fit the models to the actual measured change in wood volume related to the change in the LiDAR metrics, if that makes sense. We just subtracted 1 year from the other, the volume estimate from 1 year from the other. But if we directly modeled the damage, we would probably get a better estimate. Also, the wood volumes measured at the forest measurement plots are based on allometry from healthy trees, and then the LiDAR is looking at damaged trees to make an estimate of wood volume, and that seems like it might not work great all the time. And also, we were better at modeling some forest types than others, which brings me to my next slide. we hypothesized that LiDAR estimates would be less accurate in mixed forests, and we found that our estimates in hardwood dominated mixed forests were in fact less accurate. Those are the pink numbers there that I've highlighted. That's just a measure of percent error. And you can also see that our longleaf dominated forest types were really good. And I think that that was due probably to low damage in hardwood forest types. We just had more of them. We have more area in longleaf pine. So I think our models worked out a little bit better that way. Yeah, there was, let's see what else it is. Forest types dominated by evergreen hardwoods seem to do particularly bad. That's the hardwood pine and the mixed hardwood. And that may just be because they're pretty variable here. Like a live oak can be, its habit can be really variable. Okay, so we also hypothesized that longleaf pine dominated forest types would be more resistant to wind damage than other forest types. And we found this to be true as well. And that's just from the literature. Longleaf pine is a tough thing. Cypress seem to do really well. Cypress kind of have a lot of weight down at their base and have a really strong base from that buttressing. And so they seem to be really wind firm. Our data agreed with that. So conclusions, I'll kind of whip through these real quick. LiDAR accurately identified damage, but again, those estimates of the volume change should be taken with a grain of salt. We should do more work to see if we can model that a little bit better. We had lower accuracy in evergreen hardwood dominated forest types and better accuracy in longleaf dominated forest types. And we're speculating that may be to a large variation in tree structure. And again, longleaf dominated forests were resistant to damage. And that's in the literature. Longleaf pine is just a wind resistant species. So for future research, we've got a grad student that's working on identifying wind damage patterns in southeastern forests and trying to identify how different forests fare in severe wind events. And then, as I mentioned, if we model damage directly from measurements of wood volume change, we think we can improve our models. So that's all I've got, and I'd be happy to take any questions.
Thanks so much, Andy. What an incredible presentation. Thank you so much for this information. You've got 3 minutes, so I invite anyone in the audience, if you have a question for Andy, now is your chance to ask. Just go ahead and unmute yourself. Pose any questions. I'm checking the Whova app. It doesn't look like we have any in there, but you can also ask questions using the chat or Q&A tab to the right of your screen. Hi,
Hey,
Eric.
Andy. How's it going?
Good.
Hey, so my question to you is, how do you foresee, in terms of prescribed fire, managing all of the downwoody from Michael and whatnot? I know that they, if you burn these units, and let's say we go on the hypothesis that you need pine needles or flashy fuels to carry fire, and you start building these, how do you foresee over the long term, ingressing prescribed fire on these units over time, and then, pulling down that level of coarse woody from, your experience in the Southeast?
Yeah, that's a good question. What we did here, and I'm not, I unfortunately am not like the guy that burns direct, that actually conducts the burns, but we're in communication with them. I know that they were, really worried about those first couple of fires with with all those fuels. We didn't end up burning. We don't burn here really until about February. And so that started to dry out, and they were worried about, just really intense kind of fire, really active fires and scorching that first fire. But a lot of the coarse woody debris didn't get consumed at all, really. It's just the needles. We did a lot of salvage logging here, and we were lucky to be able to attract some loggers to come here and work on that. With Michael, just overall in the Southeast, there really weren't enough loggers to kind of help out with that. So there's a lot of places where there's still a lot of wood on the ground. And boy, I don't know, like what it's a tough question to.
Well, I mean, I just see a lot of intersections with, kind of the method you described at Jones Center, and the fact that there's these big mortality events in the West Coast, on the Sierra Nevada, et cetera, from the drought. And so ultimately, as those start transferring to the ground, it's like a different but similar problem. And what's interesting is to look at that conversion of volume from the canopy, and then, it's displacement back onto the ground. But then what do you do with it, especially if you aren't, because I would think like, down by, I know that they burned in Tyndall, but like driving through a lot of that area, I-10 South, I mean, there's a huge amount of debris that's still on the ground. And I'm just curious, if there's maybe even another fire manager in the session who could attest to what the long-term plan is to, ingress fire, and how do you, if you aren't salvaging, what do you do?
Yeah. I would throw that out there. Yeah. If somebody else has an idea.
Thanks. Great question, Eric. I don't mean to cut you both off. We just got to keep it going, but definitely anyone if you have an answer to those questions, throw them in the chat and we can keep that conversation going. Thank you again, Eric, for jumping in and joining the discussion. And Andy, I want to give you another virtual round of applause. Thanks so much. Up next, we have Emily Yurcich to share with us. She is our next speaker. Emily, I invite you to join us virtually.
Okay, great. So this is can targeted browsing by goats increase the longevity of fuel treatments in a mixed conifer forest? So this study builds off a completed joint fire science program study, masticated fuels and fire behavior in forests in the interior West. And the purpose of this research was to address an urgent need to advance the understanding of fire behavior resulting from the combustion of masticated fuels. So these fuel treatments were being used to decrease fire intensity, the flame length and rate of spread, and then to provide defensible space for firefighters, especially in your homes and in municipal watersheds. And as that wildland urban interface expands into areas likely to ignite under hot and dry windy conditions, so does the need for fuel treatments in these areas. So this original study that started in 2014 was at the University of Idaho Experimental Forest. And that's a mixed conifer temperate forest. The overstory is downy bed ponderosa pine with some Douglas fir. And the understory is a lot of ninebark, Rocky Mountain maple, snowberry, ocean spray, and several other shrub species. And so in this study design, there was 3 even-aged ponderosa pine stands were selected, and these stands were planted in 1982 following a clear-cut and broadcast burn. And in June 2014, approximately 2 hectares of these 3 stands was mechanically thinned, leaving about, taking about 30 to 70 trees were masticated. So, and that mastication was done with 2 different treatments. They evaluated the fire behavior in a fine and coarse treatment. For the coarse treatment, the operator sectioned the trees in lengths of about 1/2 meter with the mastication head. And for the fine treatment, the operator cut off the top of the tree and then masticated the tree stem and top more slowly. And the what they found was the depth of the masticated woody fuel was variable and did not differ between the coarse and the fine mastication. So, and then that after mastication in June and October, the upslope half of each stand was burned in October, the first fall following that treatment. And so that you can see the upslope in burns. And then the fuel bed conditions, kind of some images of those fuel bed conditions from that original study. During and post burn for the plots, the flame length and rate of spread they found were generally low and similar for both the coarse and the fine mastication treatments. And you can see vegetation was monitored 1 year post treatment in the burned and unburned sites, and found that species richness and diversity of plants resprouted in abundance in both coarse and fine mastication treatment following those treatments, but it was kind of variable within that. So knowing that, what was 1 year following that, and thinking about the longevity of these field treatments and the benefits of prescribed fire, which inhibits the recruitment and reduces the density of understory shrubs and small diameter trees, reduces that mid-story canopy, promotes a diverse ground flora, and reduces the fuel loading in ladder fuels. But there's a lot of problems with trying to maintain these fuel treatments with getting fire in the ground, which would be weather, seasonality, air quality standards, and smoke management regulations. And yeah, and thinking about what those shrubs are and some of those traits of the shrubs that were treated in that original treatment and what it looks like 5 and 6 years later when they start to grow back. You have the 9-bark, Rocky Mountain maple, ocean spray, and snowberry. And these species tend to restrict the generation and limit that herbaceous cover. And they form dense thickets, as you can see in this photo. They're deep-rooted shrubs. Some of them sprout from rhizomes and some from root crowns. And they have, in these low-intensity fires, have a high fire survival because they're usually top-killed, so sprouting allows them to survive. So yeah, given the problems with getting fire in the ground, land managers need more suitable fire surrogates to maintain these fuel treatments. And so that's where goats come in. And so grazing in these open canopy forests can manage vegetation that competes with trees and water for nutrients. Mastication is costly and prescribed fire conditions can be unpredictable. So the hope is that goats will be a cost-effective way to reduce that mid-story woody shrub cover, in addition to promoting biodiversity in the herbaceous understory. And the ability of plants to survive grazing or browsing is that plants' resistance to grazing and browsing. So the value of targeted grazing, it's used in a variety of rangeland applications and has been shown to be an effective tool in rangelands for reducing noxious weeds and the risk of wildfire, but limited utility and limited use and study in forested systems. But it could also be another tool in the toolkit in combination with other mechanical and fire treatments and be readily available as well. So why would we select goats? Well, they're a small hoofed ruminant animal, and they have their mouth structure allows them to consume leaves and twigs of shrubs more easily than other ungulates or livestock. They're intermediate feeders with a wide range of diets, so they can consume both woody, browse, and then herbaceous like grazing vegetation. And they can stand on their hind legs and reach different vegetation heights. They can also consume vegetation with thorns and spines easily, and they have the ability to consume vegetation that's toxic to other wildlife. Their livers and things allow them to process toxins more effectively. And then they can consume that mid-story, in this site we're able to consume that mid-story vegetation, which consists of woody shrubs. So targeted browsing, it's a tool used to manipulate vegetation, and it's usually not just it's different than just grazing or non-targeted livestock, where they can just roam wherever they want, but you're really defining them to an area with fencing. And then the purpose is to exert that browsing pressure on specific plant species or portions of the landscape. In this case, it would be those shrubs that are growing back and accumulated and building up those ladder fuels. And then the goats then can apply defoliation or trampling to achieve those specific vegetation management objectives related to the land management objectives of the forest. Yeah, and targeted browsing, it places those controls on the livestock distribution and focuses the livestock to that specific area with the fencing, herding, and supplemental placement that can be removed whenever necessary. So you can keep them from over browsing, or or in this case, when you want them to reduce all the live fuels, keep them in those areas until you achieve that percentage of reduction of live foliage. And so here you can kind of see that before image of a lot of the shrubs, and then the goats come in. And then after leaving some of that, just the remaining woody vegetation and stems in the ground, but taking all that live green foliage. And so it places those controls on livestock distribution and focuses the livestock to a specific area with fencing, herding, and that supplemental placement that can be removed when necessary. And then what we saw in this study is that goats can be effective at consuming vegetation within their browse height, and it's best when, and grazing can be best when used to maintain these field treatments when addressing vegetation with stems and small diameters that make up that 1 and 10 hour fuels. And you could see in these photos, this vegetation is probably over 6 feet tall, and you can see that clear browse height of how, when goats might be effective and when they might not to reduce those ladder fuels. There's only a certain height they can reach to consume those fuels. And so for this treatment, it was a single late season browse event that occurred in late August and September, and it was about 300 goats in each of these enclosures, and it was approximately 4 hours. So it took them to consume all of the foliage on the shrubs. And that 4 hour threshold was established at the first grazing enclosure. That's how long it took the goats to consume approximately 90% of the vegetation. And all grazing enclosures were approximately the same size. And yeah, goats would have the ability and the tolerance, and the shrubs are palatable enough for them to consume all of that vegetation. And then from July pre-grazing to September and late August when they were grazing, there was a change resulting from the grazing on those fuels from the heavy browsing of the woody shrubs, and live fuels were eliminated, and goats were able to modify those fuels like very quickly, which was one thing that we were looking at to see, will they eat these shrubs, and how fast can they consume them, and what's the utility of goats for maintaining fuel treatment. And you see there's not a lot of change in the discontinuity of the litter and duff layers after 5 hours, but there's a lot of changes in that vertical live fuel structure. So some of the benefits of using goats for fuels management goals in the short term is by extending the effects of that vertical fuel reduction, and then the surface fuels resulting from the mastication that occurred several years before still remains on the site. And some of the initial observations from that original, right after that grazing event, is that there's immediate change in the live fuels is noticeable, as you can see. goats can do a really good job at removing those live fuels quickly, and they can eat these common shrubs in the Northern Rockies. And the shrubs in treatment, these mastication and fire treatments were all still within the browse height of the goats to be fully consumed. And so you weren't having that clear mark of where they can eat and where they can't, like in some of the previous slides. And then the taller shrubs and the control sites were outside the browsing height to reach the goat, browsing height reach of the goats, so they weren't able to fully consume those. So you'd still have the tops of those shrubs reaching into the canopy of some of the ponderosa pine and Doug fir. And then goats did consume some bark and control sites, but minimally on smaller, some Rocky Mountain maple and other species. And then those late growing season plant palatability due to the advancing leaf stage and senescence did not impact the goat browsing preference. So this kind of occurred in late August, early September. So goats were still able to eat, would still tolerate those shrubs. And then there's very few conifer seedlings in these treatment sites. So there wasn't any impact to regeneration. You weren't seeing goats eating any small trees or anything. And then some of the costs from the study, thinking about some of the cost and consideration, it can be expensive to implement. And then there's a lot of physiological cost to the animal, thinking about those nutritional quality of the shrubs and how much they can tolerate. And it also requires portable fencing and like maintaining that to keep them within those areas that you're looking to target. And this study in particular used high intensity grazing for the intention to completely remove that live fuel. And we did find that it's suitable for falling fuel treatments as new growth is higher in nutrition and can maintain that fuel profile easily because the shrubs are still within their goat's browsing height. And then that objective should be well defined. Important to understand those animal preferences as well as the proper timing to meet the management goals. Thinking about when your plants are seeding or flowering, perennials or annuals. And also that these grazing things might not be compatible with other land uses depending. And then after that so all of those previous photos were initially days after that grazing event, and this is what it looks like 1 year post grazing. There's evidence of modification between the grazed and ungrazed sites, and showing that goats can influence those fuels 1 year post grazing after they've been treating, and that the target grazing can modify that shrub structure. And a plant, these images kind of show that a plant can produce leaves only at an intact growing point, and because of that heavy browse, they consume those growing points, so that 1 year later you're not seeing a whole lot of growth on these shrubs. So they really did impact those. And yes, so then when those plants' leaves are removed, its roots are also effective. So you have that excessive defoliation makes the root system smaller, and the remaining leaves are sending less of the food they manufacture to the roots. So they're really having, in the short term, they did have an impact, but it's kind of the next steps, or what does this look like multiple years after that one grazing event, or do grazing events need to be repeated to maintain this? And then what does it look like to species richness and diversity of the understory as growths come in and trample and stir up that litter and dust layer. And yeah, that's thank you. The end.
Thank you so much, Emily. What fascinating stuff. Oh my goodness. Really appreciate you sharing that with us today. Up next, our final speaker for this session is Mike Gallagher. Mike, take it away.
Right, great. So I don't know if you can see my background. I'm here in Destin Beach. I don't know where you all are, but Anyway, thanks for coming to my presentation today. My name is Mike Gallagher. I'm a research ecologist with the U.S. Forest Service Northern Research Station, located at the Silas Little Experimental Forest in the New Jersey Pinelands. And today I'm going to share some recent work that I've done with some colleagues and published on the use of QUIC-fire, a coupled fire atmospheric fire behavior model to simulate real-world fire, wildfire, and explore how other fuel structures may have impacted the Spring Hill fire. So the genesis of this work involved an 11,000 acre wildfire in the New Jersey Pine Barrens that burned in March 2019 in an area known as the Spring Hill Plains. That area historically burned in wildfires on a 4 to 8 year rotation, but was largely fire excluded for the 65 years leading up to the Spring Hill wildfire. This fire inspired a 3-day prescribed fire science QUIC-fire modeling workshop, being that it was the biggest wildfire in about a decade. This workshop was hosted by the North Atlantic Fire Science Exchange and attended by managers and scientists. And this workshop focused on 3 questions and used the Spring Hill wildfire as a real-world example in a number of simulation exercises. Some of the questions that we looked at were, what are physics-based fire behavior models? How can they be used? What are the remaining challenges to their use? And what types of questions would fire managers like to ask with these models? This last question inspired the work of this study and this presentation. And the workshop itself was recorded and can be watched at the link posted below there. Managers posed a number of interesting questions about how road conditions and natural features might serve to stop or slow fires in a simulation setting, as well as also how effective fuel treatments might be at doing the same thing. After the workshop, we whittled down the list to the following questions. How well can QUIC-fire represent the Spring Hill fire? And how do fuels that result from alternate fire regimes impact fire spread? Specifically, we looked at fire exclusion, frequent prescribed fire, and frequent wildfire. I'm not going to get into the physics-based fire behavior models in the nitty-gritty in this presentation, but basically, if you're not familiar with them, they account for 3-dimensional heterogeneity of fuels, ignitions, and fire behavior processes that can be coupled at different scales and interactive and occur, well, they're represented on a subgrid level, kind of like in this picture here, to represent heterogeneous fire spread and effects under complex real-world scenarios. And just if you're not very experienced with fire, I would say that from a modeling standpoint, any fire is complex. In the real world, whether it's a prescribed fire or wildfire, there are just about always some kind of interacting fire lines or interacting fuels. It's really complicated. So this figure just shows a number of these processes happening, a little bit of heterogeneity in fuels, how we represent them on a subgrid scale where different cells in the grid can have different processes and fuel conditions going on that are interactive. More information on this is available at the link at the bottom, or at the, at the link on the previous page. And I'm just going to give a shout out to Rod Lynn, who came up with these figures, and they're also available at the link below. There's also more information on the publication about the Spring Hill fire that we just got accepted in fire. But basically, we started the reconstruction process with a model domain. The total fire footprint is delineated in red here. However, we ended up only focusing on the first hour of the fire, delineated in yellow, before a combination of direct and indirect fire suppression activities occurred. To reduce computational time, we isolated the domain to a 2,000 by 4,000 meter area around the first hour of the fire. So that blue box there is our model domain. And just for a frame of reference, from where the fire started at the bottom of that teardrop shape of yellow, all the way up to that road on the north was about, I think about 4 miles. And the fire was moving pretty quickly. And yeah. So within this domain, we parameterized fuels, which we broke into tall forest and genetically stunted pine forest that characterize the Spring Hill Plains. And that's one of the reasons that this area used to burn historically pretty frequently, was because of this stunted, very scrubby, very volatile forest here that the wind can just whip across and carry fire quickly. So we used a canopy height profile layer generated from airborne LiDAR to identify these areas of tall and short forest. And then we used archived fuel data from prior work in the area to populate those areas. Compositionally, these areas are similar with pitch pine in the overstory and shrub oaks, blackjack oak and scrub oak, and ericaceous shrubs in the understory. And these pictures just kind of show what some of the two basically different characteristics of fuels look like during the fire, actually after the fire. There are also a lot of sand roads throughout the burn area, throughout the domain, which we also incorporated. Many of these roads were infrequently used. Again, you can also see them in these fuel pictures here, and were narrow and made for pretty poor fuel breaks against the head fire. What was interesting is that during the actual fire, these roads did stop some flanking fire. We represented all the roads similarly with a 5-meter fuel break, which we considered was about average. The wind data was the trickiest part. Despite there being 3 heavily used weather stations near the fire, none of them really sampled data ideally for fire spread simulations. Obviously, fire spread simulations wasn't the intended use of any of these weather stations, probably more for aviation and agricultural purposes or just the general public. They're all available online. But it's worth keeping in mind that just because you've got a lot of local weather stations that are available doesn't mean that the weather data that they collect will be very useful for modeling. Basically, the tower closest to the burn, right there at that airfield to the north, only samples wind every 30 minutes, which for the 1-hour segment of the fire that we were trying to sample provided pretty much no resolution in wind variation. The tower to the northeast sampled wind at 1-minute intervals, which was great, but clearly reflected a local wind pattern that differed from that which was observed during the fire. You have to realize that in New Jersey here, even though it's a pretty simple landscape and it's flat, there's a lot of local features that can cause some variation in winds. One of them would be some of these water features that you see around the area around the fire. Also, we're not that far from the coast, and so there can be a sea breeze that'll set up, but it doesn't always push all the way inland. So there might have been some influence from that was affecting it. The tower that we ended up using was the one on the southwest here, and that one had a 5-minute interval, and it still wasn't perfect. One of the challenges with that one was that the wind direction data was only recorded in cardinal directions. So basically, we got north, northeast, east, etc. One of the challenges with this is that it made for unrealistically choppy wind changes. We ended up using that data, but we performed a smoothing function on it to make the wind less choppy. The other thing we noticed that we believe with all 3 of these towers is that they were actually oriented to true north rather than magnetic north. Magnetic north rather than true north. Our declination is 12 degrees here in New Jersey, so it's enough that you could easily make that mistake, but for a simulation purpose, 12 degrees can cause quite a different outcome. So we corrected for that as well. The resultant weather matched pretty much what we expected, given our observations during the fire itself. So we evaluated the footprint of the simulation by comparing the predicted footprint with the observed fire footprint at 1 hour. We found that 69% agreement, which is the green area. We found 25% over prediction on the flanks, which are the blue areas, and 6% under prediction at the head, which was the yellow area. We also compared the paths of the fire in terms of distance traveled, the distance from the point of origin to the farthest point in the fire. And for both cases, the simulation was 6% shorter in terms of distance traveled and distance from the origin to the farthest point of the fire. So we considered that pretty good, a 6% shortfall, essentially. The model also outputs resultant fuel layers, or a resultant fuel layer. And this visually had similar unique features that were observed in the field. One unique feature that can occur during a wind-driven wildfire in these forests is something called what we call tree crown streets. And you can see that in the photo on the right here from the aircraft. You can also actually see it. Let's see if we can. You can also see it. Those tree crown streets are basically these artifacts at the edge of the fire, these linear features that you can see in the image. So the model actually showed them as well at the edges of the simulation output, which we thought was pretty neat. So the Spring Hill fire burned under fire excluded conditions, but we want to explore how prior burning, repeated wildfires would have changed this, changed the way this fire behaved. So we reran the fire with fuel structures known to be generated from repeated wildfire, repeated prescribed fire, under varied understory fuel loading and structures that relate to those conditions. So essentially we looked at wildfire structure, frequent prescribed fire structure, and I'm sorry, that should have been a fire exclusions structure, prescribed fire and wildfire. And we vary the fuel loading by 50% in some of them to reflect how prescribed fire can change understory fuel loading. And we got our canopy structure shapes from some work that was done previously by Nick Skowronski. Basically, Nick and some of his collaborators did an analysis of fuel structure and fire history in the Pine Barrens, looking at prescribed fire history and wildfire history, and found that frequent wildfire tends to compress the forest down into the understory fuels, basically compress the canopy into the understory fuels, while frequent prescribed fire raises the canopy and reduces understory fuels. So we're able to take structures from this and impose them in QUIC-fire using the same fuel load or reducing it by 50%. This table just shows basically a matrix of those different conditions that we simulated. And this is how the different fire footprints looked in their outputs from QUIC-fire. This is 8 of them. There were actually 2 more, but you get the picture. They all look fairly the same in shape from at a glance, but there's actually some pretty significant differences in their distance traveled and their widths that are pretty interesting. So, so this table summarizes the differences in the burns in the last slide. And basically on the left here, we have fire size. And on the right, we have average and maximum rate of spread. And these are ordinated by fire size, but you can see how fire regime influenced average rate of spread or forward growth of the fire. So, so basically, like I said, their rate of spread is the forward growth of the fire. And what we can see is that this varied with the forest structure. Basically, the areas with frequent prescribed fire had the lowest rate of spread. Areas with the with a wildfire history had a faster rate of spread, and the areas excluded had the fastest rate of spread. You can also look at rate of growth, which takes into account the entire fire's rate of growth, kind of like an amoeba growing at all sides. And this accounts for lateral growth as well. And what we can see here is that fuel reduction really had an impact on that lateral or total rate of growth. We could summarize that looking at this table here that basically just puts that all together, and we can see how these different attributes, basically a frequent prescribed fire, no frequent prescribed fire, or fuel reduction, change different aspects of the fire outcomes, basically rate of spread, rate of growth, or fire size. In the ideal situation where we had a prescribed fire structure and a 50% fuel load reduction, there was over a 50% reduction in fire size and spread growth overall. So so it seems like most scientists and managers think about these sorts of simulations as a way for guiding fire operations, in the sense of, how do I manage my prescribed fire without losing it? And a more interesting question might be, how effective will my fuels management be at accomplishing its goal of reducing risk in a wildland urban interface? So this map shows a neighborhood a few miles from the Spring Hill fire that would have been in danger if the wind had shifted west. And this risk map on the right is something that we published a few years ago in IJWF, and it illustrates risk at the border of the neighborhood that's surrounded by a fairly continuous pine forest that basically connects to where the Spring Hill fire was. Simulating proposed fuel reduction treatments and then testing how they stand up to subsequent hypothetical wildfires is an alternate way that these models can help guide management. For instance, how big does the thinning need to be? Do homeowners even own that land that needs to be thinned? How well will standard homeowner guidelines for reducing fuels work? In this map on the right, we can see that land ownership at the wildland interface is complex within different buffers around a home that represent different guidelines for management. And on the right here, we can see basically two different, or sorry, on the left, we can see two different profiles that could be incorporated into QUIC-fire that reflect either unmanaged or managed fuel. Finally, I'd like to give a plug for some work that my colleague Louise Loudermilk presented earlier today that relates. We're working together to develop some new, easy field-based remote sensing methods with U.S. Fish and Wildlife and U.S. Forest Service, USGS, and the Tall Timbers Research Station that managers can use to quickly collect fuels data that can be used to parameterize these models and evaluate risk at the urban interface. An added bonus is that this laser-based approach can also be used to estimate burn severity and fire effects, which happens to be the theme of my talk on Friday. There's a link to one of Louise's recent presentations that really synthesizes the Spring Hill fire presentation and some of this other fuels work that we're doing. It's a really great presentation, and the link is at the bottom of the page here. I'd also just like to really thank the folks who worked on this together with me. Zach Cope and Daniel Rosales-Jaron really did a lot of work on, they did all of the modeling work. They run QUIC-fire, and they did a really wonderful job at this. Also want to thank Trevor Rayner and Tom Gerber, who were the IC and Ops chief on the Spring Hill fire. And they really were critical in that workshop that spawned this work, and they also were really helpful in setting up and parameterizing the simulation. So I want to thank those guys, and Kevin Hires, Rod Lynn, Nick Skronsky also all helped. And I want to thank Amanda Mahaffey and Virginia Shute of the North Atlantic Fire Science Exchange who put on that workshop that really spawned this work. Thank you.
Mike, thank you so much.